In this episode, we'll be building two Raspberry Pis with light and thermal sensors attached for data logging. We'll process these log files with the goal of automatically tracking my work and sleep habits. This episode is a mashup of hardware, programming, and some data analysis with a text editor, SQL, and some spreadsheets. For those new here, at the start of 2019, I started my own business via this website where I'm releasing weekly screencasts on sysadmin and DevOps topics. So the high-level goal of this data logging project is to track my work and sleep habits over the next few months based on my presence in particular rooms. I wanted to do this since starting a new business can be really stressful, and I wanted to track how my work and sleep habits were affected. Let me explain how the data sensor works. Say I'm in my office and I have one of these Raspberry Pi based sensors mounted on the wall. I'm using double-sided tape and I have it stuck about 7 feet high. Well, this is a stock image of what my office might look like. So on the first sensor connected to the Raspberry Pi, I'm capturing how much visible light there is in the room. For a state like, are the lights on or off? Then on this second sensor connected to the Raspberry Pi, I'm capturing thermal data for a bunch of points in that room. Then I can use this data to capture the state of, okay, the lights are on, but is someone actually in this room? It would look something like this if you were to project or overlay the sensor's thermal detection grid onto the room. So in each of these 64 cells in this 8x8 grid, you can actually measure and record the temperature readings for those cells. For this example, say I was sitting at my desk, you'd see much higher temperatures in these cells where I'm sitting, where the orange indicates a higher temperature and the blue is colder. Then on the Raspberry Pi, all I'm doing is continually logging these sensor readings at 1 event per minute. In a day, I'm collecting 1,440 event readings, broken down by 60 events per hour times 24 hours. Based on the data that's logged, I can then create a bunch of graphs for, hey, were the lights on in this particular room, and hey, was there someone actually in this room? Then I can use this to roughly guess my total hours worked in a particular day. But you can also get things like start and end times, maybe break times, and then you can start to graph this across weeks and months. To give you an idea of what this thermal data actually looks like when visualized, check this out. Here's a quick data capture of me walking into my office and waving at the sensor. You can see it's totally pixelated as it only gives you 64 data points, but this is actually all I need. Having less data is actually nice here, in that I was originally thinking of using something like OpenCV for object detection or maybe creating an ML model. But it turns out I just wanted to check a few specific pixels to see if the temperature was high enough, and then use that to determine if I was actually in the room. This is super simple and it works without being too complex. Obviously, this is highly tuned for my specific use cases and rooms, as I know the layout and where the grid is sort of overlaid in the particular room, and then can trigger events off that data. So that covers my office, but I also have the same sensor in my bedroom too. For this second sensor, I have a long USB cable and LED breakout board attached to it as well. I'm using this as a type of smart nightlight in addition to the data logging functionality. Basically, the added nightlight functionality here can detect if the lights are on or off, and if I get up in the middle of the night and the lights are off, flip the nightlight on so I can see where I'm walking. Let me explain. So this is my bedroom. Well, this is a stock image of what my bedroom might look like. Again, this sensor is continually checking and logging data from the points in this room. I can then use this to track my sleeping patterns based off my room presence. The sensor can see when I'm in the room based off the temperature or thermal data, even when the lights are off. But for this added nightlight feature, I can say if the lights are off and a heat value in these particular cells is consistent with someone being there, then trigger the LED for a set period of time. This nightlight feature was sort of an afterthought, but it totally works really well as I can turn the lights on within 100 milliseconds of someone being detected there. What I like about this is that it's totally passive from my perspective. The sensor's just sitting there in the room collecting data, and then you can do sort of clever things like, hey, if a human's detected here, flick on the nightlight. I'm sure you could do all sorts of cool stuff with this type of platform, but these are just the problems I've run into as I've been using this. All right, so now that you know what the high-level device looks like and what my use cases are, let me walk you through this in a little bit more detail. By the way, all this code is up on my GitHub, along with a detailed build log, which you can find in the episode notes below if you wanted to replicate this. First, I'm using a Raspberry Pi Zero wireless model. This is a super small Linux computer that's about the size of half a credit card with Wi-Fi support. This picture here actually doesn't do it justice as this thing's super small, it's tiny. I purchased a kit on Amazon that has a Raspberry Pi Zero, a case, and a power adapter. You also need a micro SD card for installing the base OS and the detection software. I also needed to find a bunch of tiny adapters for things like micro HDMI. This costed a few extra bucks since I didn't have these cables around, but you only need power once the device is all configured, as you just connect to it via SSH over the network. Next, I'm attaching this light sensor that will return a value for how much light it senses. This is just a float value that you can easily log. I purchased the TSL2591 sensor from Adafruit, and it works seamlessly with the Raspberry Pi. You just connect it using the I2C bus, and I soldered it on. Once you have this device hooked up to the Raspberry Pi and it's configured, it will return a few values where you can calculate the lux visible to this device. The Wikipedia page says lux is the derived unit for measuring the amount of luminous flux in that particular area. Basically, I just think of this as the light the sensor can see. You get a float, and you can see if the lights are on or off. If the lights are off, you get a 0 value, and when the lights are on in my office, I get a value of around 30. So it's super easy to log and plot this data. Next, we have the thermal sensor, which grabs 64 temperature values in an 8x8 grid at up to a distance of around 20 feet. I purchased this AMG 8853 sensor from Adafruit and connected it to the Raspberry Pi using the I2C bus too. Personally, I find the Raspberry Pi an awesome platform for playing around with this type of stuff. This is one of the first projects where I've actually connected sensors to the device, and it went pretty smoothly. There's tons of sensors you can connect to it too if you browse around this website. Pretty much the sky's the limit. So the sensor is pretty low resolution, but in addition it can only capture 1 frame per second or 10 frames per second, and that's configurable. For my office, I'm only capturing at 1 frame per second and logging the data at 1 event per minute. For the bedroom sensor, I'm running this in 10 frames per second mode, since I want to trigger the nightlight really quickly. But again, I'm only logging the data at 1 event per minute. You can think of this like a thermal camera like a FLIR, but it's very limited resolution at only 64 pixels. You can read all about the theory of thermal imaging on the Wikipedia page too. Kind of a cool story here is that we used to have one of these high-resolution FLIR cameras at work, and you could touch your hand onto a table and then remove it quickly. Then you could point the FLIR camera at the area on the table where you touched, and you could see a clear hand imprint. Since it raised the temperature slightly in that area, it was pretty crazy. Alright, next on the bedroom sensor, I attached this LED breakout board for the nightlight logic. I had a few of these RGB LED breakout boards that I was using from a previous project. It's called a blink stick, and it's basically just a LED you connect via USB, and then you can program it to trigger the light. I was using this for notification alerts and things like that. They cost about 15 bucks and work great for giving visual indications for automated programs. And they also support lots of programming languages, so you can sort of integrate it into your workflow. So as I mentioned, I'm logging the sensor data from both these sensors at 1 event per minute. And that's going to a local file on the Raspberry Pi. So I've had these devices up and running for about 3 months now collecting data. And when I want to look at the data, I just SCP the log file off the Raspberry Pi and then process it on my laptop. That's not automated right now, but at some point I'd like to maybe stream this data and then automate the analysis process. I also wrote a simple web server that's on the Raspberry Pi that sits on my local network, and you can get a real-time view for what these sensors are seeing. I use this heavily during development to quickly debug things. For example, I wanted to check the light values when I flick the lights off and then when I flick the lights on. I also use this heavily to make sure the thermal sensor was actually pointed to where I was in the room, to sort of get the bounds for the viewing area when I walked into frame and when I walked out of frame. The code for all this is posted up on GitHub. One's for the sensor program and one's for the nightlight. I wrote all this using the Go programming language, but this did create a problem though, as the sensor driver didn't exist in the Go programming language, so I ported the one from Python to Go. You can download the driver for this too and recreate my setup exactly. So why didn't I write all this in Python versus Go? Well, I've been using Go as my personal programming language, and I'd never worked with I2C stuff before, so it was more of a learning experience than anything. All right, so let me show you the web interface for a minute. So this is a live reading of what the Office sensor is seeing right now. You can see the timestamp, the lux or light value, which is the visible light in the room, and then down here there's the thermal sensor data being plotted out into an image. What's cool about this is actually a project that allows you to run GNU plot in JavaScript, and then I'm using this to plot the data. So you can see down here the values and the script that I'm using to generate this image. So you can tweak all these values and have the image change live. This was kind of cool when I was debugging, as I could try different color tones and see what worked. I can't really express how having this web server helped me greatly while I was debugging this. For example, changing the position of the sensor to get good readings. I was mostly using this on my phone and sort of walking around the room and reloading the page to see what it looked like. This is how I was able to find the pixels of where I was in the office and sort of trigger the detection logic off that. I use the same technique in my bedroom for detecting pixels for when I should trigger the nightlight. All right, so now that you know how the Raspberry Pi and sensors are set up, let's take a look at the logging data. When I was originally setting this up, I wasn't sure how I wanted to visualize the data, so I just logged it in JSON format. It turns out you can actually import raw JSON into BigQuery and have it auto-detect the schema and set up tables so you can run queries against it. I'm using BigQuery here since I use it for a lot of other data analytics stuff and it's sort of familiar, but you could honestly use whatever you wanted to since it's in JSON format. So here's what the log file actually looks like. You can see the timestamp, the thermal pixel reading data, and then the lux value. That's basically it. And they're captured at 1 event per minute. Personally, I like exploring the data using SQL since you can do all sorts of grouping and sum calculations with ease. So let me show you what that looks like. From here, I created a few charts. First, I wanted to see if I could get the lux data plotted across time. Next, I was asking myself, can I determine if lux is over a specific value, say 30? Can I determine if the lights are on or off for that period of time? Then group this into minutes, and then get a sum for how many hours per day the lights are on. Next, let's do the same thing for thermal data. Can I count how many hours per day a human was detected in the room based on temperature readings for specific pixels in that grid? Next, let's plot both the lights on data and thermal data into a single overlapping chart. All this is still pretty early as I just started looking at this data after logging it for a few months, but it mostly works and I think it's good enough for what I need. So let's look at the data in BigQuery along with the spreadsheets as I have this stuff plotted out already. I have all the SQL queries in the episode notes below if you wanted to replicate this. By the way, BigQuery is Google's data warehouse product. You can literally process petabytes of data with this thing really quickly. So this is totally overkill for my needs as my log file is only 50 megs. But I was just familiar with it, so it's the same whether you have petabytes of data or megabytes. So I just imported the raw JSON data into BigQuery, and it automatically detected the schema and created this 2019-01-02 office table for me. You can see the schema here. We have our timestamp, lux, and thermal pixel data. Then we can preview what the data looks like. What's cool about BigQuery is it has all your normal data types, but it also allows you to store a struct or array natively inside a table. So this is where I can store my thermal data, and I can actually query individual pixels right with SQL. Here's a query for getting the total amount of light seen per day. This is sort of a sum across all the minutes in a day. This is more of a building block than anything else. I downloaded the results of this query in CSV file format, and then imported this file into a spreadsheet where I could graph it. You could also export this data directly into a spreadsheet, but I wanted to download it onto my laptop to explore it with a text editor. But this is just my workflow, you could do it either way. So you can see in the graph here that we can clearly see the amount of light per day, and you can kind of see it going up and down, which is pretty cool. This is sort of more of a proof of concept than anything as I was exploring this data. Next, let's run a similar query on the thermal data, where we're going to sum it up into a total per day. You can see the query results down here. I did the same thing, exported to CSV, and then imported into a spreadsheet where I can graph it. But this is not actually all that useful, as it's not getting me to the result I wanted. I want to get the hours per day that I was actually in that room. So after a bit of trial and error, I finally came up with a SQL query that did what I was looking for. Basically, get all the events where the light value was over 30. This indicates the lights were on. Then group those events per hour and give me a sum per day of how many hours per day the light was on. And you can see the results here. Then let's go and graph it. So I was looking at the data in real time periodically on my phone via the web server, but I only looked at this data log file after about 3 months using SQL. So you can see here there's a bunch of low values. I was definitely working a lot of hours during this period as I just launched my subscription service. My thinking is that during this period of time, I was doing a bunch of testing in my office with acoustic panels. I was trying to get a really quiet space where I could record audio. And one of these panels must have been obstructing the view of the sensor as I was logging it. So during this period of time, the sensor values are likely lower. So I might have to amplify the data in this window, but I'm still thinking if I even need to care about that since it's working correctly now, and what's that extra work going to actually get me? Anyways, you can clearly see in this graph we're getting a total hours per day where the light's on, which is pretty awesome. These values can now be used as a proxy to calculate roughly how many hours per day I'm working, which is pretty awesome. Next, let's do the same thing for light and thermal data together. Basically, count how many hours per day the lights were on and someone was home in the office. You can see the results in the preview here. Again, I downloaded the CSV file and imported it into a spreadsheet to graph it. Now you can see the lights on graph here, the thermal detection events per day here, and then an overlapping graph of both data sets. So you can see the graphs mostly match up. So this is where I'm at with the project today. And I probably need to tune this a little bit better. As you can see, the graphs don't exactly line up, but maybe that means the lights are on and I wasn't in the office, or I was in the office and the lights weren't on. I don't know. But this mostly works as a proof of concept. This will allow me to track my work and sleep habits. But what I'm not showing here is that I ran all the same graphs for the sensor in my bedroom, so I can also plot what my sleep schedule looks like over the last few months. Obviously, this doesn't tell you the quality of work or sleep in these periods, but it can act as a guide. So what's next? Well, I want to create some type of dashboard that will show me this data automatically in real time. It'd also be nice if I could get some sort of automated email where I could sort of log what I was working on the previous day, how many hours I think I worked versus what I actually worked, and what I worked on. And then I can also log the quality of my sleep. What I'm hoping is that this will give me useful patterns over a few months. Also, I want to get something where I can tell the specific hours worked into some type of 24-hour heat map versus just grouping the data into totals like this. This would tell me what times I was typically working and sleeping. I know many of these hours I work are typically later in the day or early morning, so it'd be nice to sort of visually see what this pattern looks like. But overall, what I like about this project is it's totally passive and it just logs this data for me, and I have total control over it, especially for privacy reasons. Anyways, hopefully you found this interesting, and if you're looking at doing something similar, this might work as an initial prototype. As I mentioned before, you can find all the links to all the code and a build log down below. All right, that's it for this episode. Thanks for watching, and I'll see you next week. Bye.